Hello. We are going to discuss today sampling distributions. We need to understand, first of all, what are the different sampling methods, how we use sampling for creating sampling distributions, and why sampling distributions are extremely important. Because in conjunction with the use of the CLT theorem, the central limit theorem, it allows us to approximate parameters for populations, for different populations. When we run an experiment or we overview an observation, then what we need to know is what event or outcome will occur when we complete that. The only way to know that, to find out, is to take a sample from the population, meaning we need to take a subgroup, a smaller part of the population, and focus on that part. Well, there are many reasons why it is important to consider samples than the entire population when we are reviewing properties and we try to find trends in different data sets. One of the reasons for that is that sometimes the population is humongous. We are not able to handle it as is. While other times the population is something that is unknown. For example, population about the evolution of a specific species over the billions of years that Earth exists. Or the population may be ever-changing, such as the population of microbes, for example, that it is never constant, it always changes. So we will not be able to find, let's say, the average of the diameter of a microbe, if it is circular, because we are not going to ever be able to have to capture the entire population. So for these reasons is why we use samples. And samples are nothing else than simpler, smaller subsets of the population. Sometimes we get confused between sampling methods and data collection methods. These are two completely different things, although they both refer to data. When we refer to data collection methods, basically what we mean is how can we collect all the data of the population, meaning census. Think about census. What census tries to do is to capture all the information about all the citizens of the United States. We're not focusing as a subset of census. Census is a great example to understand the difference of a population and of a sample, and understand also why sometimes it's not enough to sample. For 2020, I can give you an example. For 2020, that we have the regular census for the United States, we knew that this census will cost more than $5 billion. Because of this situation, although I don't believe that it costed that much, because of the pandemic, we didn't have people that they went around, so we had to complete everything online and send everything online. Nevertheless, each one of us should have completed the census application in order to get for the government to get all the information for all the citizens and residents of United States. Now, the census is used not only for demographical reasons, not only to understand how the population of the United States is distributed, but also to define legal issues, to define how we distribute money to the different states or to the different zip codes, to the different neighborhoods. Who is in more need for, let's say, ESL programs, so where we have a lot of immigrants. What areas are are overpopulated? The density of the people that they live in an apartment is bigger than the rest of the country. So there are many reasons and there are many different factors that need to be captured if we try to understand the population of the United States. There are so many different factors, and this data set is used by so many different organizations, institutions, and the governmental agencies that a sample is not enough. A sample would capture some of the trends and characteristics of the population, but not all. That's why, in this case, we want to have a data collection method to collect all the data for the population. While sometimes, as we already discussed, it's better, it's simpler, or it's less expensive to select only a sample and focus on that sample in order to better understand the population. Right here on our slide, you can see the different type of data collection methods and the different type of sampling methods that exist. Although we're not going to focus right now and talk further about each one of those, nevertheless, we are going to discuss the simple random sampling because we will assume in most of our class that we will be working with samples that they have been collected, selected from populations from using the simple random sampling technique. Now, everything that we know and we care about for an entire population, we care about the sample as well. And what do I mean by that? Well, think about the population right here. And this is a population of a specific variable. We consider different measures for tendency, the mean, the median, or different measures for dispersion, the variance, the standard deviation. Or maybe we want to understand a little bit trends of the population, so we may consider the proportion of, let's say, the different genders that they are represented in population when it has to do with consumption of different foods, or something like that. Anything. So this is going to be also the proportion. All these metrics or measures, we call them measures in statistics, we call them metrics in most other business, science, and commerce, are considered to be parameters when you refer to a population. So when you have the entire set of data, then you refer to them as parameters. Why? If you focus on only a sample of the population, let's call this sample 1, and you refer to the same type of measures, mean, median, variance, and so on, then you are going to be referring now not to parameters, but to statistics. So when we say and this is now statistics, and what we are using as the title of our course until now is nothing else than a measure. This is what it is, a measure of a sample. So this is what a statistic is, a measure of something, mean, median, mean, median, proportion, standard deviation of a sample, not of the entire population. So that's the difference between parameter and statistic. So what I want us to do right now is to make sure that we know what is the notation for those. So when we refer to parameter, the mean is considered to be the mu. The variance is nothing else than sigma square. So we start with the standard deviation that is sigma, and the variance is sigma square. The correlation, that is nothing else than R. And we will also talk a little bit further about correlation later in our class. And the proportion, that is expressed with P. Okay, so these are the symbols that we are using for the parameters. Now, when we refer to statistics, meaning measures that come from samples, we have the same names like the ones that you see here, but the difference is that we are using different symbols. So for the mean, we call it X bar. For the variance, we call it S square. Standard deviation is S. correlation, I'm sorry, I mixed up this. The correlation for the parameter for the population is rho, the Greek letter rho, while the correlation for statistics for a sample is R, and the proportion, as I said, is P, while for the statistics is P hat. And sometimes if we have two different samples or two different populations, we are using the letters PQ and P hat and Q hat. From now on, we will be using this notation in order to, whenever we talk about statistics or parameters, please memorize that because it is extremely important to know what you're talking every time. And a sample is, we handle it in a completely different way than we handle a population. And when we refer to a parameter, we have different theorems and different formulas that they apply than when we refer to statistics. So if I say the mean of a group of students of UIC, and I'm referring to just a group of the population, and I talk about the statistics. So if I want to take the mean, the average grade of a group of students of UIC, then I'm talking about a statistics, and I will refer to that as X bar. When I refer to the entire body of UIC, then I will refer to the average of their grades as mu. So let's look together at one example. Find incomes of people from Illinois. We talk to 10 people. So that's our experiment. We take 10 people. We stand on a corner of Halstead and Taylor, and we ask them to tell us about the income that they get. Then each person is represented by a letter. Let's say we are talking about a person X1, X2, X3, up to X. X10. And actually, these are going to be the incomes, and the incomes of these 10 people would be Y1, let's say, Y2, Y10. Okay. Now, these are the actual incomes of these 10 people. This is going to be a sample. A sample from what? A sample of the population of Illinois. Okay, and we're taking only 10 people in here. And another example, and they are represented by X1 up to X10. These are the people that are coming from the 10 million people that they live in Illinois. Now, in the same way, we may have what? We may have the population of their incomes. The sample right here for the incomes, again, will have values from Y1 to Y10. Now, if you consider these values right here, you can get their average. The mean of these Y1s to Y10 will be nothing else, if you think about it, as the sum of Yi divided by 10 in this case. Right? And what is this? This is the mean. With what mean? The mean of the incomes of these people. So how many of them? 10. What is this? That's a sample. So I declare it as X bar. This is the mean, and it's a statistics. Now, I didn't want to use this mean, right, to identify, to approximate the parameter. And what is the parameter here? The mu, the parameter of income of all the people in Illinois. This sample has characteristics. This sample is very specific. How did we get this sample? We just stand on a corner of Halstead and Taylor, and we didn't move because we didn't want to go away. We were just bored. So this is a convenience sample. And as a convenience sample, it's supposed to be biased and it's supposed to be non-representative of the entire population of Illinois. Nevertheless, it is a sample of that population. And the X bar is the mean of that sample. and the X bar can be used to approximate the mu of the population, of the income of the population of Illinois, although probably the result will be completely unsuccessful. So the first thing that we need to understand is that we do have samples. We do use samples. You are not going to go around and talk to all the 10 million people of Illinois in order to get what? An average of their income. You are going to get a sample. Now, how you select this sample is important. It is important if you want the result that you get to be representative of the population that you consider. Let's look at a different example. A soda machine is designed to dispense, on average, 240 milliliters per drink. We want to discover if this is accurate. Many times, this is a real-life case scenario, and it is a real-life case scenario. Why? Because people do want to really calibrate their machines and to have to know exactly how much will this machine dispense, how much of the product will this machine dispense. So if we want to calculate that, if we want to see if this machine is calibrated, then what we need to do is to actually take a sample. Take a sample from this machine, and let's consider this sample to be 40 different drinks. Okay. From the sample, we calculate the average. So you take the sample, and the average is 236 milliliters. Okay, what does this mean now? Well, 240 milliliters is what you want the machine to dispense. 236 milliliters is what this sample shows you. Now, if you look at this data one by one, you may discover that some of them, they will be at 241, 242, 248 milliliters, and some of them may be at 236, 235, 231, 230 milliliters. So there will be a range of volume for the drink that it is dispensed by this machine. The average for the specific sample, that is a big sample, 40 drinks, is 236. So this 236 is nothing else, if you think about that, than your X bar in this case. Okay, now X bar. While the population average, the one that you want this to happen, you are not sure that this is happening, is 240. So this is the mu that you want. Okay, so that's one thing that you need to keep in mind. Now, by looking at the 40 drinks and looking at the average of these 40 drinks, do you really believe that this means that you are okay? Are you close enough? Is this 236 too close to 240? Well, it's 4 milliliters away. What is 4 milliliters? It's almost 2.5% away. Well, if you go with improbable events, 2.5 is a good approximation. So it seems to be close enough to what you want. But is it enough? This is what we are going to do for the next 2 weeks, when we will basically apply the rules and the theorems that we know in order to estimate, in order to make estimations. Okay, so the whole point right here is that are you losing money by accepting this as your the dispenser of your machine? If you are the person who owns this machine, are you actually having angry customers that they don't like the fact that they get less drink than they should? So these are considerations that you need to think of every time that you calibrate the machine. And the data that you get are from these samples. Okay, good. Okay, now this is one sample. In order to be sure, what you may want to do is get another sample. In order to compare the samples now and the averages of the samples, you want the other sample to have, again, 40 drinks. With two samples, if the one was at 236 and the other, let's say, was at 250, can you get an idea? Well, no, they are far away. So You may want to get a third sampling. And what about if the third sampling gives you 260? Probably you are going to get a fourth sampling. What about if the fourth sampling gives you a 234? Now you have two of them that they are quite small and two of them that are quite big. Probably you're going to continue. So how many samples you're going to get in order to decide, it really depends on the problem, and it really depends on the samples that you're getting. The whole point right here is that samples are very important. And when we discuss about sampling distributions, and we refer to sampling distributions, then what this means is the probability distribution of a statistic. Oops, confusing. What does this mean? Well, think about the entire population of drinks that are dispensed by this machine. Let's assume that the drinks that they are dispensed from this machine per week, let's take it by week, is 1,000 drinks. Okay, now if I consider 40 of them, this is a sample. If I consider another 40 of them, this is another sample. Now, if I consider a third sample, that some of them belongs to the first sample, some of the drinks. Some of the drinks belongs to the second sample, and some are new. This is a third sample. The question is, how many different samples can I have from this population with size 40? Well, the truth is that if you calculate them, it's nothing else than 1,000 choose 40. Quite a few. If you cut this number right here, that is huge, it's going to give you the number of different samples with size 40 that you can get from the entire population of these 1,000 samples. This is, now if you take the means, the average what? The average dispensation of the drink that you have for each one of the samples. So a total of many, we are talking about how many? These many means, these many averages. Then what you get is nothing else than a set of averages that each one of them represents the average for a sample. What samples? All the possible samples that you can get of size 40 of this population. So the vector of all these means is giving you the probability distribution. This is the sampling distribution. So the sampling distribution is what is the probability distribution of those means that you have in this vector. Let's graph it. Let's try to understand it by graphing this. So what do you have right here? Think about that. What you have is, first, the population. The population has 1,000 drinks. You consider what now? All SIs that have size 40. Why do I call it size? Because each one of these samples right here have what? Have size 40. Are they distinct? Are they unique? No. They can be like this. So all the samples right here, how many of them? A total of 1,000 choose 40. If you want to calculate that, you can calculate it, and we may want to calculate it so you can see that from a population of a total 1,000 data points, we go to a population of what? Well, let's see. We are going to a population of 1,000 choose 40 points. How many are these? 1,000 factorial. Where is my factorial? Divided by what? By 40 factorial divided by 9 960 factorial. The result is 5.55 to the 7 times 10 to the 71. So you can see right here that we actually have a lot of points, just too many points. You see the number. Okay, so if you want to have a mathematical expression for this number, just in case, it's going to be nothing else than 1000 factorial divided by 40 factorial times 960 factorial, right there. So a huge number. It's equal to 5.5 times 10 to the 71. What is this now? This is a set. A set of what? A set of samples. S1 sample, S2 sample, S3 sample, as what? If we call this number A up to SA samples, too many samples. So we went from this population to this. What is this? This is a set of all the samples that we get of size 40. All of them. Okay, now what do I do now? Now I take these and I am going to image this to what? Well, I'm going to image that to another set, and let's call this set right here, right? Let's call this SP prime. That for each one of those samples, I'm going to consider the X1 bar, meaning the mean of those. So the mean of dispensed drink for sample 1, for sample 2, for sample 3, for sample 4, for sample 6, for sample 8. How many do I have? Too many, these many. These many what? These many means. These are the means. So if I consider this set right here, over here, is nothing else than the data set of the means. Now, if I consider the probability distribution of these means, of this set, then this is what I call a sampling distribution. I hope that it makes sense. If it doesn't make sense, please go back and re-listen these last 5 minutes, because it's important to really understand what is a sampling distribution. You start with a population. You consider a size for your sample. Then you take all those samples in there, and for each one of them, you consider the mean. You may consider something else than a mean, because the sampling distribution may be of any parameter. So it can be the mean, it can be the standard deviation, it can be the proportion, it can be the variance, it can be anything. The whole point is that it is a parameter. So you consider now these numbers, that each one of those correspond to a sample. But you have to remember that you have to consider all the samples. This is what we call sampling distribution. Okay, so I just wanted to take this time in order to really explain to you what is a sampling distribution, because we will be using it all the time from now on, so it is extremely important to really know what it is. Okay, given the fact that you have already reviewed and made sure that you understood what is a sampling distribution, now we are going to enter the area of central limit theorem. Central limit theorem is extremely important. It is extremely important because we use it every time that we apply any kind of estimation, we run any kind of hypothesis testing, and we want to make sure that we use it when it is appropriate. Okay, so the first thing that we need to make sure that we understand is that the central limit theorem is applied when we use sampling distribution. So for now, we will be focusing on sampling distributions of sampling means, just in case that we get confused. So sampling distributions of sampling means, exactly as I explained it before. what the central limit theorem tells us, it tells us that, let me read it, what you have in the screen. It says that if x bar is the mean of a random sample of size n from a distribution with a finite mean mu and a finite positive variance sigma square, then the distribution of z equals to x minus the mu, the mean of the sample divided by the standard deviation of the sample divided by the square root of the size of that sample, it approximates the bell curve. Is this clear? No, it's not. I know up front that it's not. Okay, let's see what this thing tells us. Let's try to decipher what this thing tells us a little bit. What it says is basically that if I have a population P right here, and this population P, I take samples x1, x2, x3, xn. I'm sorry, these are not samples. These are points in the specific population. So if I consider a population P and I take these points from x1 to xn, and I consider these right here to be a sample S, and the size of this sample S is equal to n, then what I know is that x bar is the mean of this sample of S. This is what I know. And I also know now that if I consider this x bar, I can also write it as mu x. If I consider the mu x to be the mean of this sample and the sigma x to be the standard deviation of S, then what I know is that x for any x minus the mu of x divided by the sigma x square root of n, this is nothing else than a z-score. This is what this tells us. So basically, before we knew what? Before, what we said is that whenever you have a population, the entire population, and the population follows a normal distribution, then x minus mu of the population divided by the sigma of the population is a z-score. Now you know what? You know that if you have a sample from that population with some kind of size n, then we also have a way to translate out of that sample to the normal distribution. And the translation formula is the one that you see right here on your screen. This is nothing else than the formula that we use to translate between what now? Between samples that they come from a specific sampling distribution to the n, to the normal distribution. Let's try to see an example so we can understand it better. We have a population. Okay, up to here we are good. We have a population of different elements. Out of this, so this green box is the entire population. We know that the population has mean mu and standard deviation sigma. Now we are taking sample 1, sample 2, sample 3, sample 4, sample 5 of the population. How many samples do we have? Well, it depends. It depends on what? Assume that we're taking all the samples have the same size. Okay, let's call this size n. So if my population has, let's say, T elements, T of all of them, then the samples that you have to create, x1, x2, x3, should be T choose n. Then you're going to have all the possible samples with size n out of your population. Now, after you do that, you consider what? You consider the sampling means. The sampling mean for each one of these samples. So we are saying that the mean of the samples is mu x bar. What is this? The mean of the samples. The mean of all the samples. The central limit theorem tells us that the mean of all those samples is equal to the mean of the population. And it also tells us that the standard deviation of the samples, of the sampling means, that is the sigma x bar, is equal to the population standard deviation divided by square root of n. This is what we know. And this is what we call the standard error of the mean. So, let me recap here. The central limit theorem tells you two things. It gives you some relation between the mean of the sampling distribution and the mean of the population. It also gives you some relation between the standard deviation of the sampling distribution with the standard deviation of your mean, of your population. The relation is the following. The mean of the means of your sampling distribution is the same as the mean of the population. And the standard deviation of the means of your sampling distribution is going to be equal to the standard deviation of the population divided by the square root of the size of the sample. So when the size of the sample becomes bigger and bigger and bigger, then what we get is that the sample distribution, the standard deviation of the sampling distribution becomes closer to the standard deviation of the population. Let's try to look at an example. A simple example here. The population values are 1, 3, 5, 7. What are these? These are written numbers on slips of paper. So we have paper and we write 1, 3, 5, and 7. 2 slips of paper are randomly selected. So 4 papers in an urn, you just select 2. Okay, what is the probability to get a 3 and a 5? What is the probability to get 1 and 1? Because it's with replacement. What is the probability to get 3 and 3? Well, the whole point here is to create this probability distribution. Let's do it. Let's make sure that we create this probability distribution. We will do that. First, what we want is to find the mean, the variance, and the standard deviation of the population. So the mean is 4, the variance is 5, and the standard deviation is 2.236. Do you believe me? No. Let's see a graph in order to better understand it. Well, the probability to select, when you select a piece of paper, the probability to select N1 is 25%. To get a 3 is 25%. To get a 5 is 25%. And to get a 7, 25%. Equal probabilities. Uniform distribution. Good. Now, we want to select 2 pieces of paper. So, right here you have the pairs of all the possible values or that they will appear in these 2 slips of paper. So it's going to be 1, 1 or 1, 3 or 1, 5 or 1, 7 and so on. What are these? These are the values that you get for each pair. Good. Now, these are your samples. The first one is the first sample. 1, 1 is the first sample. 1, 3 is your second sample. 1, 5 is your third sample. and so on. These are samples. Samples of what? Samples of 2, size 2, from what? From your population 1, 3, 5, 7. That's what it is. For each one of those, I find what? I find the mean. So on the orange, let me do it right here. On the orange column right here, the numbers that you see are nothing else than the average of the numbers that you have right here. 1 plus 5, 6, 6 divided by 2, 3. So for each one of these, and these are what? Each one of those are the possible samples that you can have. What samples? How many are these? Okay, let's count them. How many samples do you have? 1, 2, 3, 4, 5, 6, 7, 8. So you have 16 samples. Where did you find these 16 samples? Well, these are 16. You have 4 values, 1, 3, 5, and 7. You have 4 values, and out of these 4 values, you choose 2. So this is going to be 4 factorial divided by 2 factorial times 2 factorial. That is going to be nothing else than 4 times 3 times 2 divided by 2 times 2. So you choose right here, 4 choose 2. And then what you do is you multiply it by 2 because you can have them in the one next to the other. The one, but you have what? You have unlimited number of choices. So because you have replacement, this is incorrect. It's not going to be 4 choose 2. I am sorry for that. This is going to be, because you have replacement here, so in this case it will be nothing else than 4 squared, and 4 squared is 16. This is how you get the samples. Okay, so based on that, what we have right here, we have all these different means. Okay, so you can put them in one vector, all these means together. Let's do it. Let's put the means together. Okay. Well, I say right here that I put the means together and I find the probability of these means. So how many different samples do I have that they have mean of size 1? Let's see. I have only one of them. You see it? I have only one of them. Which one is it? This, right here. I have only one sample with size 1. So 1 over 16 is the probability to get a sample out of my sampling distribution that has a mean of size 1. In the same way, how many do I have that they have mean 5? Let's look at them. 1, 2, 3. 3 5s here. They correspond to these, and these. What are these? 3 different samples. So the probability to get a 5 as my sample mean is 3 over 16. What is this? This is the probability for what? The probability for your x bar to be equal to 5. This is what you get. So now what I do is I create the probability distribution. So here you look at the probability distribution. For each one of these possible means, this is the probability to get them. Okay, now if you look at that and you want to calculate the mean, the variance, and the standard deviation of the 16 sampling means, you can use what? You can use the formulas that you know to find the expected value and the variance for a probability distribution. So what you do is that you perform what you know on how to find the average, how to find the mean. And you remember, for a distribution, in order to find the mean, you take the sum of the xi times the probability that corresponds to this xi for all the i's from the first value, that is 1 in this case, to 7. So you add up those products and the result is 4. And then you perform the similar kind of calculation that will give you the variance, that is x minus the mu that you just find, the 4, squared times the probability for the xi. And you do that again for all the xi's from 1 to 7. So if you perform these steps, you will get the following numbers. So these are the numbers that you calculate if you apply the formulas that you know for the mean and the variance and the standard deviation for the distributions. Now, what I want you to see is that the mean is 4, the standard deviation is 2.5, and the standard deviation is 1.581, and the variance is 2.5. Okay, now, if you remember what we did before is that we calculated the mean, the variance, and the standard deviation of what? Of the population of the 1357. And we have them right here. Right here. So the mean of the population is 4. Yes, of course, 1 plus 3 plus 5 plus 7 divided by 4 is 4. And the same way, we can calculate the variance and the standard deviation. You remember those numbers. Okay, so the first thing that I want you to see now is that, well, as you can see, the mean now that we calculate for the sampling distribution, that is this right here, is the same as the mean that we have for the population. This is exactly what the central limit theorem tells us. That if you take the standard deviation, the sampling distribution, you find for a specific size all the means of the samples, and you take the mean of those means, then this is equal to the mean of the population. But also, it says a different thing, and this is the following. It says that if you take again this sampling distribution and you take the standard deviation of what? Of those means, then the standard deviation of those means will be nothing else than the standard deviation of the population that we calculated before to be 2.236 divided by the size of your sample. That is this. And this is basically a proof of the central limit theorem working. It works, it's true, and it's true for any distribution. That's the beauty of it. This is what we are going to discuss in the next slide. So before we review the central limit theorem, what I want us to see is now look at this. What is this? This is the histogram for the probability distribution for this sampling distribution of x bars, meaning I'm talking about the probability distribution of the means of the samples that we created, those 16 different samples. Do you see that? Does it remind you anything? Well, if you think about that, it's very close to be right? Normally distributed. And it's true. This is the whole point right here. The whole point is that no matter what you start with, and before we started with what? Remember that the population that we started with was the population of papers, pieces of papers, that they had 4 numbers on them, right? And we had 1, 3, 5, 7. So we started with a uniform population distribution, and with the translation that we did through the sampling distribution, we managed to create a sampling distribution that is what? It is normally distributed, okay? And it's normally distributed right here, as you can see, is the sampling mean that is 4, and we calculated the standard deviation to be 1.581, okay? So if you take x minus 4 divided by what? 1.581 right there, then this is going to be the set of z-scores. This is going to translate to the bell curve. This is what we know. This is what the CLT theorem gives us. And this is quite important. Why it's important? Because basically, look at what's happening here. You start with a distribution that may have any format. It may have any kind of strange look. Like, for example, the one that you see right here. Or it may look like this. It doesn't matter how it looks. The whole point is that if you start with a population, this is your population, and it looks like that, then if you take a sampling distribution, meaning from the population you take samples, all of them, of a specific size, 15, and you consider the means of these, the means, as you can see, these are the means, then the sampling distribution of those means is going to be to follow what? The normal distribution. It's going to be normally distributed. And this is what the central limit theorem says. Well, the central limit theorem tells us, give us some restrictions, and this is what we want to also understand here. Does the central limit theorem works always? Not really. Not really. It doesn't work always. There are some conditions that need to be satisfied in order for that to work. So first of all, the first thing that we need to understand is that if we start with a population that is normally distributed, then we will end up with a sampling distribution that is also normally distributed. That's for sure. Okay, so we have no issue with that. The other thing that we know, though, is that we may start with any type of population, such as this. Right here, that shows you that any kind of population that we start with doesn't need to be normally distributed. If you take a sampling distribution and the sample size that you use for that sampling distribution is samples that they have size greater than 30, then the sampling distribution will be normally distributed. While if you start with a normal distribution, then the sampling distribution of any n will be normally distributed. So if you start with a population that is normally distributed, you don't have any restrictions. If you start with a population that is not normally distributed, then you want the sample to be greater or equal to 30. That's important. Okay, before we continue and see other restrictions and limitations of central limit theorem, let's look at an example in order to see how do we apply it, how do we use it. So we have a cellular phone bill. We have cellular phone bills for residents of a city, and the mean of them is $63, and the standard deviation is $11. Random samples of 100 cellular phone bills are drawn from this population. So how many do we have there? I don't know how many we have there. What I know is I get samples of 100 cellular phone bills. Okay. If the mean standard error of the mean of sampling distribution, in fact, what we want to do now is to find the mean and the standard error, meaning standard deviation divided by the square root of size, in order to understand better my sampling distribution. Okay, let's look at the problem and how we are going to solve. First of all, we do know that the mean of the population is 63. $63. They already told us. So if they already told us, then we can take it for de facto. It's something that we know. Good. Because of the CLT theorem, we know that the mean of the population is going to be equal to the mean of the sampling distribution. So the mean of the sampling, the mean of the means of those samples now, of this 100, of size 100, is going to be 63, because they told us already, right? So be careful, because this type of example right here, it goes backwards from the examples that you will see. What we do is that we have information for the population, and we are taking now what? We are taking a sampling distribution, and each one of these samples have size 100. This is what we know. But we know that the population has a mean that is equal to 63, and we know that the standard deviation of the population is 11. So we know this. So can we look at the population, at this sampling distribution? Well, central limit theorem gives us two types of information. What? That the mean of that, this is what it is going to be equal to the mean of this. We already have it, so it's going to be 63. So now I know that the mean of the means is equal to 63. And the next thing that I know from the central limit theorem is that if I divide the standard deviation of the population by the size of the sample, square root of the size of the sample, then I get the standard deviation of the sampling distribution. So let me write it out. The standard deviation of what? Let's call it sigma x bar of the sampling distribution okay, is equal to what? To the standard deviation of population. This is what is the sigma divided by the size of the sample. So you can see right here that if you take a very, very small sample, then the standard deviation of the sampling distribution is going to be equal to the standard deviation of the population. If the sample becomes bigger and bigger and bigger, right here, this number at the denominator becomes bigger and bigger and bigger, so the standard deviation of the population of the sampling distribution becomes smaller and smaller and smaller. This is what happens right here. Now, let's look at the examples that I have, and let's look at the graphs for the sampling distribution and for the population. So right here, I know that the population that I have of all the cell phone bills is almost what? Almost, no, they don't even tell us that, but we can say it. It's not normally distributed, but it behaves like normal. Okay, we can see that. Almost normal. Okay, and I have what? I have the standard deviation for that, and I also have the mean of that. And then what I do is I consider the sampling distribution of what? Of phone bills, of 100 phone bills. So I'm taking samples of 100 bills at a time. And I take all of those samples of 100 bills at a time. Then what I know is that the mean of that sampling distribution will be 63, and the standard deviation will be nothing else than 11 divided by 100 square root of 100. Well, if you look at that, what do you see? You see that, first of all, the standard deviation is smaller. So this one is much smaller than that. It's almost 10% of that. This is what you see right here. Why? Because I have a very big size. So I normalize right here. I normalize what? My standard deviation in order to fix the setup, to fix the form of my distribution. What else do I see? I see that the mean is exactly at the same point. You see it, 63, 63. Well, now, does this affect anything? Well, you will say just a moment. This is much slimmer, if you look at the shape, than this one. How are these the same? Well, they're not the same. They're similar. they have the same trends. And why do you care? Why is it slimmer? Well, it's not slimmer. If you think about that, it's not slimmer. Why? Because it has many more points, many more data points. You remember the data points right here is of the form of what? I have, if I have 10,000 customers here, if I have 10,000 customers, then what I have here is 10,000 choose 100. That's huge. Okay, so this is a small, I have zoomed out in order to be able to see the shape of the distribution. So this is how I want you to compare those two, if you think about them. Okay, let's talk now about the central limit theorem implication and limitations, because there are implications and there are limitations of the central limit theorem. Remember that we start with any type of distribution, any type of distributed population, and we have to take a sample size that is greater or equal than 30. This is what the book says. Well, we haven't explained yet the importance of greater or equal than 30, but I can tell you that this means that we need to get a sufficiently large sample. This is what it means. A sample that is not going to affect the standard deviation. That's the reason of that. And then once you do that, then the mean of the sampling distribution will be equal to the mean of the population, and the standard deviation of the sampling distribution will be equal to the standard deviation of the population divided by square root of the size. Now, if you have different types of formats of distributions that you start with. And right here I have some examples to see them clearly. If you have a population that behaves like that, Poisson, it looks like Poisson. It looks like, I don't know, it looks like exponential, let's say. Okay. Then the sampling distribution, meaning the distribution, the probability distribution of the means of that population, of samples of that population, when the samples have a size greater than 30, it's going to look normal. So is this strange? Yes, it's strange. We start with something that looks like that, and we get to something that is normal. The example that I gave you is something that looks like uniform, and I proved to you that it looks like normal, even with less x's. We had 16 there, we didn't have 30. And even if you start with something that has this strange shape, and it's possible to have this strange shape as a distribution, again, you're going to end up like normal. Of course, if you start with something that is normal up front, then definitely you will end up with something that is normal, if you get a sufficiently large sample. The thing here that you need to remember is that if your sample is small, like for example right here is equal to 3, then in this case that you start with something exponential, you're going to have it skewed. It's not going to look like normal. If you start with uniform, it will look like a triangle. If you start with a U shape, it's going to reverse the shape of the U shape, but it's not going to look normal. So slowly, as you increase the sample size, you get closer to normality. Exactly as we saw before with the binomial distribution. When we discussed about the binomial distribution, we said once the requirements are satisfied, NP greater than 5 and Q greater than 5, then it can be approximated by the normal distribution because it looks more like normal. Same thing here with any kind of distribution that you start, population that you start with, and the corresponding sampling distribution. But, as I said, there are limits. There are situations that we cannot use the central limit theorem, convergence. There are limitations that we know that there are distributions, and I can give you an example of a distribution that is not going to turn normal easily. Like, for example, if you have a distribution that looks like that, right here, and at the end, for whatever reason, it has some outliers. Right here, it has outliers. This distribution right here, if you get a sampling distribution with a size of 30, it's going to look like this. So it's going to be skewed to the right. In order to achieve normality, the x must be greater than 200, 300. So you need to increase your size, the size of your samples, a lot in order to achieve normality. But we will talk about that later. So the whole point here is to talk a little bit about the mean. When do we use the CLT theorem? So the CLT theorem is used most of the time when we have a large enough sample. In the case that we have a large enough sample, then the standard deviation of the sampling distribution is very close to the standard deviation of the population as well. We will see that. Pretty much, the rule of thumb is the following. The rule of thumb is the one that your book says. If your sample is greater or equal to 30, and you have a population that is not normally distributed, then if the population is symmetric with few outliers, then you get a normal distributed sampling distribution. If though your your population, your initial population is asymmetric with few outliers, again, you're going to get a normal distribution if you get a big enough sample size. But the truth is that if you have outliers, everything changes. So for our class, for the rest of the problems that we will be solving together, we will focus on examples that we have few outliers. And this would mean that the central limit theorem will be applied and we will get a normal distributed sampling distribution if the size of the sample is greater than 30. So right here, what I have done is I have run an actual example in order to show you a little bit more of how it looks like if you get one specific distribution, one specific population that at the beginning, the mean of the population was 3.5. This is what I had. I ran it for 10,000 trials, and the mean for 10,000 trials was 3.49. So slowly, what happens is that the mean converges to the mean of the population. Okay, let's look at another example. The training heart rates of 20-year-old athletes are normally distributed, with a mean of 135 beats per minute and standard deviation of 18 beats per minute. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution, and then sketch a graph of the sampling distribution. So the first thing that I want us to remember here is that we know that we have what? We have the mean of the population. We have the standard deviation of the population. We already know that the population is normally distributed. Now, we take random samples of size 4. Oops, size is small. Yeah, the size is small, but we already know that we started with a normally distributed sample population, so the size is not an issue anymore. It's not a limitation anymore. So what does this mean? We apply the CLT theorem for that, and it will work just fine. So if we want to know what is the mean and the standard error of the sampling distribution, remember, standard error is sigma divided by square root of n. So it's going to be 135, meaning exactly the same with the mean of the population that we have right here. and right here, and the standard error will be nothing else than 18 sigma divided by square root of n. That is 18 divided by square root of 4. That is 18 over 2, that is 9. Okay, so pretty much if I want to look at it and look how it looks, this is how it looks like. The population is normally distributed, the sampling distribution looks like that, right? If you compare it, you can see the difference on the curves. The curve that I had before, it was more flattened, right? It was not as thin and tall as this one. Why? Because the sigma before was 18. The standard error for the sampling distribution is 9. So we have a difference on the sigma. And the sigma is basically what tells us how far away we are from where? From the mean. The mean stays the same, 135, but the sigma becomes smaller. You remember? 1, 2, 3, right here. So the sigma becomes smaller right here. The standard error is the sigma for the sampling distribution. So what happens? What happens is that the points that they are at the tails of that come closer to the mean. Why is that? Well, remember that we're talking about samples here. Samples of what? Samples of these 20 athletes. You have 20 athletes, choose 4. You have a total of how many different samples here? 20 factorial divided by 16 factorial, that is equal to what? It is 20 times 19 times 18 times 17. It's almost 20 to the 4th. We're talking about 400 times 416, 1, 2, 3, 4, 6. This is the number of points that are samples and means right here. While on the previous beautiful curve that we looked at, that was the curve of the athletes, we had only 20 athletes in here. So from 20, we went to 160,000. That's why the curve is changing in order to consider that these samples that they are at the end are samples that they show the heart rate and they are what? They are far away from the actual mean because these are bad samples. Okay, that's why in order to standardize, to normalize my what? My distribution right here, what I do is I make sure that I make the standard deviation smaller. And here we can see a different example. Let's look at this example as well. 50 drivers from age 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Assume that the sigma is equal to 1.5. Do we know that the initial distribution of all these drivers is normal? No, we don't. Can we use the central limit theorem? Yes, we can, because the sample size is greater than 30. It's 50. Okay, good. What does CLT tell us? That the mu is equal to the mu of the population. That's the one thing. Do we know the mu of the population? Well, it's equal to 25. And what about the sigma? Well, the sigma is going to be equal to, the sigma of this distribution is going to be equal to sigma divided by square root of n. So in this case, the square root of 50 is 0.21213. This is what we know. Okay, so we have already the mean of the population, the initial population, and this is the information that we get. Now, what do we want to do? We want to find the probability that the mean time is between 24.7 and 25.5. This is what we want to calculate. How do we calculate that? Well, in order to calculate that, what we need to do is consider again the translation formulas. What I want you to pay attention is that since we are talking about now what? sampling distribution, we have a sample, then we need to consider this formula for translating from x's to z's, right? From x's to z's, we use this formula that also considers the size of the sample, because the denominator here is going to be the standard error in this case and not the standard deviation. Remember, if we are starting with a population, we are using this formula. When we start with a sample, we use this formula. We apply the numbers that we have. We get our two numbers right here. These are what? These are the z-scores. So if I want to go for probability from 24 points, I'm sorry, for speed, time spent, 24.7, 5.5, and I know that is normally distributed with a mean of 25, I want basically to go from this to the bell curve. Remember, bell curve. What is the bell curve? N 0,1. This is your bell curve. Okay, good. So what you need to do is use this formula to get what? To translate each one of these values into z-scores, right? And this value right here into a z-score, right there. So I find my z-scores. And what's the next thing that I need to do? Either go to your table or use R and do P norm of what? Of 2.36 minus P norm of negative 1.41. And this is going to give you the result that you get right here. Now, one thing that we need to understand is that if we don't know the population is normally distributed, then we really need to know the sigma of the initial population in order to actually calculate the standard error. This is something that until now it was given to us, but it is possible that it will not given to us. The truth is that we rarely know this sigma, because this is a matrix, this is a parameter of the population. How would we know that? Well, in book examples and in book problems, you do know it. In real life, you rarely know. So what do? Well, in the case that you don't know that, then you need to make some assumptions. If your sample size is greater than 30, and you already know that it's greater than 30, some books say 40, but our book says 30, and we are going with this. So if your sample size is greater than 30, then you can assume what? You can assume that your sigma that you have for your sample is equal to your sigma. You can assume that, and you can continue from there. Now, you cannot assume that if the size is less than 30. If it is less than 30, then you cannot use the normal distribution. So what do you use? You use a different distribution that we call the student distribution. The student distribution, or T distribution, is similar to the normal distribution, except of the fact that it has lower standard deviation and fatter tails. So in terms of graph, it looks like the normal distribution, but it has a fatter tail. We will see some format. The other thing that you need to understand is that the student distribution is not only one curve. We have many different curves. So student distribution is a family of curves. There are actually many different T distributions. But we do care for the first 35, 40 of them for now, for our class. Why? Because after the first 30, each one of these normal curves, each one of these T curves corresponds to the size of your sample. Now, if you have a size of sample greater than 30, you're not going to use the student distribution. You're going to use normal distribution. If the size of your sample is less than 30 and you don't know the standard deviation, you're going to use the T distribution. So the the number of the size of your sample determines which curve you will use. And the size of your sample relates to the curve in the following way. Each curve in the T distribution has two identifiers. The one of the identifiers that we care right now is called degrees of freedom. The degrees of freedom is the size is related to the size of your sample by this formula. So you are going to use, if you have a sample, let's say, of size 16, then you are going to use the curve with degrees of freedom 15. This is how we determine which curve to use. I hope we have some time to talk about the degrees of freedom later, but it relates basically to the number of independent variables that you have in your data set. And when we are talking about variables, we're talking about one variable with different values. When we have a sample, let's say, of 45 elements, then and we try to approximate the metrics, the measures of the population based on this sample, then we depend on the sample. So the first thing that we know is that if we have 45 data points in the sample, only 44 of them will be independent. That 45th will depend on the previous one. And because of that, we have the degrees of freedom. And because of that, we have the relation of the degrees of freedom to be nothing else than sample size minus 1. If you want to look at your curves, the curves look like this. As I said before, it's a family of curves. So you expect to have many different curves right here. The normal distribution is this black that you see right here. This one is the normal distribution, is the n 0,1. You can see that right here, what you can observe is that these curves, that they belong to the family of curves of the student distribution, it happens to be what? Fat. You see them? They are fatter. Now, the higher that the degrees of freedom become, as you can see, the red one corresponds to degrees of freedom 3. The blue one corresponds to degrees of freedom 6. Now, if I had degrees of freedom 10, 12, and so on, it's going to approximate slowly what? It's going to approximate slowly the black curve that you have right here. And remember, the black curve is nothing else than what? Than the normal distribution. So as you move, let's say that this purple that I created right here is of degrees of freedom equals to 20, right? The closer you go to 30, you will find yourself on the black curve. So this black curve is approximately equal to the curve from the T distribution where df is equal to 30, approximately. There are some differences, of course. Now, also, the way that we read a T-score table is different than the way that we read a Z-score table. The reason for that is that, as I said, for the normal distribution, we have only one curve. So all the information, all the probabilities are on the table. When we work with a T-score table, it's as if we work with 5, how many? 1, 2, 3, 4, as many as columns, 5, 6, 7 different normal tables. This is what you should think. But we're taking only one column of them, and that's it. So we try to approximate again. We are not going to be able to be very exact on our calculations when you will use a T-score table. So what do? Assume that you want to find what? You want to find the T-score right? That corresponds to a probability equals to 0.90. Okay, so the probability, the curve will look like this. I want somewhere here, I want to find this point, that is the t-score, where the 90% of the entire t-curve is going to be to the left of that, CDF for the t-score. So what I need to do is come here, inside the table, try to find the come on the top, not here, on the top, in this column, and find the 0.9 right here. So you know now that the t-score that you are looking is right here. Okay, what else do you need? Well, you need the degrees of freedom, because I said that there are many different curves. So you need to know what is the size of your sample. Suppose that the size of your sample, the n, is equal to 21. What does this mean? This means that your degrees of freedom is equal to 20. So now you will go right here at 20, and you will come right here at this point, and this is what? 1.325. What is this 1.325? The t-score. The t-score, that corresponds to what? If you are looking for the probability for your t to be less than this, to be equal to 0.90, then your t is equal to 1.325. This is how you calculate it. Now, we are working, as you know, in R. The way to calculate to find t-scores in R is with the QT. So in this case, you will enter 0.90, that is the probability that you want, and the degrees of freedom, that is 20. If you want to find the corresponding probability for the t-score, then you would do the PT. And this would be the PT of what? Of, let's say, 1.963, and then comma, the degrees of freedom. Always you should enter the degrees of freedom. And then for this case, it will return the degrees of freedom is equal to 1. If it is equal to 20, is 1.963 equal to 20, will be somewhere here. So it will return the probability at around 0.96 in this case. So this will be approximate 1.964. And this is how you will calculate that. Okay, we are going to continue with more examples and playing around and calculating P-scores, P-scores, talking a little bit about the CLT theorem, and solving problems that they require sampling distribution, along with reviewing R code on sampling distribution on Friday. Thank you very much, and see you in class.